Hello, Calculus students. Today we are looking at a second application of integration. In this case, we're finding area between curves. So far, we have looked at how to find the area between a curve and the x-axis. And what we're doing today is adding a second curve and talking about what we do to get the area between these two. This drawing may make that seem like it makes sense to you. And I hope that it does, because if you found the area of one curve and then found the area of the second curve and then subtracted those two, that would indeed tell you the area between those two curves. Well, I guess my job is done for this video, and that's all set. I joke. All right, so we've got two different curves going on here. We've got y equals x squared over 2 plus 2, and then y equals negative 2x minus 1. We can tell that x squared over 2 plus 2 is the curve on top because it's the parabola, and that negative 2x minus 1 is the bottom because that's the line. So let's find the area under each of these curves. So we've got the integral from negative 3 to 0, those are the bounds I'm given, of x squared over 2 plus 2 dx. And we're going to find the integral from negative 3 to 0 of negative 2x minus 1 dx. This is a great place for us to really think about some ways to make our lives a little bit easier. We've been spending quite a bit of time doing antiderivatives by hand, and that's great. This is a great place to talk about how to do them using some kind of technology, whether using Desmos or using a TI graphing calculator. Any of those things can be done without too much trouble using either of those things. On Desmos, if you go into functions, which is under the keyboard, there's a miscellaneous functions, and you can see an integral symbol that would let you type these things in pretty quickly. If you're using a TI graphing calculator, it's going to be under the math menu. It's down towards the bottom. It's going to be called FNInt, which would let you, if you have a newer TI, again, do that visually without much trouble. If we're not doing this using technology, and this one I will do by hand, what we need to do is make sure that we do the antiderivative. So that's going to be x cubed over 2 and then over 3, so it's over 6, and then plus 2x, evaluated at 0 and negative 3. So that's going to be 0 over 6 plus 0 minus negative 27 over 6 plus negative 6. My 0 parts go away, and I'm left with, so that's going to be divided by 3, negative 9 over 2 minus 6 more is going to be negative 21 over 2. Minusing, we got 21 over 2 is our final answer. Okay, for the other one, we're looking at negative 2x minus 1, the antiderivative of which would be negative 2x squared over 2 minus 1x, and we are evaluating that at negative 3 and 0. Again, we're going to have 0 and then minus negative 2 times 9 over 2 minus negative 3. Okay, that's going to give us negative 9 and then plus 3, which is going to be 6. So if we do 21 over 2 minus 6, we end up getting 9 over 2 as our answer. Just to verify that on Desmos, again, I'm going to type in that same thing, going from negative 3 to 0, and we're going to do x squared over 2 plus, I have to make sure I don't mess up my fractions, plus 2. And when we do that, we get the same exact thing. I will give you a warning if you're using Desmos. You have to put parentheses in the integrand. That is the stuff on the inside here. And if you were to start typing int while you're in a command line, it'll bring up that symbol. All right, let's look at another one. And again, for these ones, the setup is much more important than the actual evaluation. So for the remainder of these problems, I'm going to assume that you're going to use some kind of technology to evaluate them. And I'm going to show the setups on here, but not necessarily the evaluation steps. So in looking here, this time the line is on top. So we're going from 2 to 3, and that's going to be 2x plus 1. And then minus this same interval from 2 to 3, and the parabola is the x squared, so x squared minus 8x plus 10 dx. This is the setup. You're doing the antiderivative at the top minus the antiderivative at the bottom using the bounds that we have, and that will tell us the area between these two curves. And when we do that, we get a value of 9.666 or 9.667, depending if you're truncating or rounding. In the AP Calc, if you're using this video to help you prepare for that, we need to take things to 3 decimal places. It doesn't matter if we truncate or round. If you would prefer to leave this as a fraction, that's 9 2/3, which would end up being 29 over 3. Looking at the next one, we've got the same thing, except here we have an issue. Because this functions change which one is on top at this point. Thankfully, we can clearly see that, but we got to be a little bit careful when we set this up. So I'm going to call this kind of a left region and a right region here. So going from -3 to 0, we can think about this as the line minus the parabola. And then going from 0 to 1, we can think about this as the parabola minus the line. So we do have to be careful when setting that up just because of that. I've also written these in kind of a different way. I've combined these into one integral each, and that's okay as long as we use parentheses. We know that we have an integral property that says if we're adding 2 integrals, we can combine them as one integral with those things added together, and that's totally fine. So let's get the set up. So we've got -3 to 0, and I'm going to name these things f of x and g of x, which is going to help me when I use Desmos because I can use those as code. And the line is going to be f of x. My parabola is going to be g of x. And then we've got dx. For the other part, we're doing the same thing. And we're going from 0 to 1. And now we've got to do g of x minus f of x dx. So when I put this into Desmos, we get 9 for the first part. And for the second part, we get 3 2/3, which is going to be 11 over 3. That's my final answer. We've got another one where we have a split. This one I'm just going to do the setup. I'm not going to actually evaluate this. Because again, the evaluation steps are all the same. I can see where this is joined, but I just want to make sure that that's accurate to what I'm seeing. And I want to remind us that if we want to find an intersection for something, in this case x squared over 2 minus 3, and -2x plus 3, we can set them equal to each other. We can either do this graphically, or we can do this using some algebra. I'm going to do the algebra approach here. Multiply that 2 by everything just to kind of make sure we're on the same page and bring everything to the same side. So we've got x squared, it's going to be -6, so -12, plus 2 is going to be plus 4x because we're multiplying everything by 2. That's going to factor into x minus 2 and x plus 6. And we can see that we have one of our points when x equals 2. The other one would be at x equals -6 when these things meet back here somewhere. Okay, wow, even kind of accidentally wrote that almost exactly over -6. I love it. Cool. So for our setup, let's call our parabola f of x and our line g of x. We're going to go from -1 to 2. And for that one, the line is on top. So g of x minus f of x dx. And then to that, we're going to add the other interval going from 2 to 4. But switch these around, so we got f of x minus g of x dx. At this point, if you've set these up in either y1 and y2 on a TI calculator or in Desmos using f of x and g of x, you input these values and you are done with this problem.